Yes, I'm Hobson Lane, and there's a little update. Last week I was hired as the head of artificial intelligence at IRA, so you don't get to blame me for their chatbots ineptitude at the moment, but it's getting better. We're using it currently to onboard blind customers who are using our device to help them see the world in a different way, to enrich their lives by helping them, guiding them through their lives. Currently using human agents, but as time goes by and I have some more time to build the bot, we'll be using the chatbot to help them through their lives in the same way that OnStar helps people in Lincoln Town cars get through the day. So you'll want to clone this repo. This is where all the slides are, some of the data that you can use during the workshop, and also some of the code, so the Jupyter notebooks. And the notebooks folder is probably where you'll spend your time. That's where I'll be spending my time during the demonstrations. First, I'll talk a little bit about deep learning, my perspective on it, and try to, everybody has their own view of machine learning and deep learning and their relationship. I'll talk about different chatbot approaches. I have a different view than Mariah had in her keynote speech, but we're going to be focusing on one particular type of chatbot as we go through the demonstration. And then we're going to incorporate prosocial feedback into that bot so that it can be a little more kind and gentle than, say, Ty was at when Microsoft launched her. Let's see, we'll do it once I finish discussing that and some of the challenges of doing that and adding that prosocial feedback, we'll start you off on building a chatbot. Building a chatbot, making it social. The first part of social is being reasonably intelligent and competent. So the first part of the workshop will just be building a chatbot. A really simple form of a chatbot called a retrieval-based chatbot. And then we'll gradually expand it with greater capability and subtlety by using semantic search for that retrieval. And finally, we'll experiment with some prosocial ideas. Artificial intelligence. In my mind, it's the same as machine intelligence. I prefer machine intelligence to artificial intelligence because it's more positive and it tells what it is rather than what it's not. It's certainly not natural, but it's definitely a machine doing the thinking. It's some sort of intelligent behavior that we can get out of a machine. In order to do that, we need to do not just a little machine learning, but a lot of machine learning. So really, AI is just machine learning squared or cubed or plus plus or whatever you want to call it. It's a lot of machine learning, and that's what makes AI. It doesn't have to be deep learning. It can be any model. In fact, many of the models that some of the breakthroughs that happened in deep learning were quickly imitated with conventional models that were actually more efficient and better at it than neural nets. So neural nets are great, and deep learning is awesome, but not necessarily synonymous with artificial intelligence. However, in the world that we live in and the press the way it is, they've latched on to deep learning as being equivalent to artificial intelligence. So that's my view on those terms, just to get us all on the same page. So machine learning, of course, I'm sure you're in an intermediate session, so this won't be any surprise to you. But we'll be talking about taking inputs and turning them into outputs. That's all we're doing. So in the case of trying to build a carnival trick performer that's going to guess your weight based on your height, we would have to give it a lot of examples, and so we'll be feeding our machine learning model a lot of examples of appropriate dialogue and intelligent dialogue, and that's how we'll train it using machine learning. Some of the approaches that have been used in the past, all the way back in 1965 or maybe even 1964, depending on when you think that Eliza was born. But she was the first psychologist or therapist chatbot, and she was built at AT&T and based largely on grammar or pattern matching approach. So that pattern matching approach lived on through up until the 70s. And we started to experiment with retrieval. This is when document retrieval, information retrieval became a thing. And so we started to use it in order to build comparable chatbots to Eliza, but using a bit more extensive database of possible statements to say. And so she could be a little more, have a bit more variety in her conversation than she could in the early days. After PC Therapist, we moved on to Jabberwacky, got a little more broad, and we have more data in 97, and that's the end of the dot-com boom, or actually in the peak of the dot-com boom, so we had a lot more data on the internet. And so Jabberwacky was a lot more fun, but still quite wacky. Chatbot came in to play more recently as a more retrieval-based bot built by a high school student actually, and I'm going to show you how to actually install it. It's actually it's evolved as he's evolved to be quite an awesome platform for building chatbots, in Python at least. Alice started the trend towards ontology-based or knowledge-based or logic-based chatbots. So these are kind of similar to rule-based chatbots, and that's where Maria and I sort of diverge ways. I think of retrieval-based bots as using essentially text search or web search to find the statements they want to say, whereas pattern matching is using grammars to generate or recognize features. They can, however, be blended with ontologies and knowledge bases in order to populate those templates with other information, like she said, about the world. She called those grounded models when you use an ontology or a knowledge base to inform the statements and populate the templates that the chatbot is saying. Generative models. This is when things got ugly. Generative models can be a lot more creative. They rely only on the statistics of words. And as Maria said, they can get caught in loops. They can be easily trained off the rails by maltreatment of users. In the case of Ty, that's what happened. She was just trying to be popular, and they made sure that popular meant being cruel. And so her audience did. And so that's how she went off the rails. So generative models can be difficult to control. They're difficult to explain. They require a lot more data. You can see on the right-hand side just a general impression of how much data is required as we've moved through time. As we've gained more data, we figured out ways to use it, but then these models require that data in the end to be proficient at dialogue. And so Smart Reply in your Gmail system, that's a hybrid system using both generative and retrieval-based techniques. So it's using retrieval and also an ontology, of course. So when you ask for the sports score for a particular team, or if it's using information about the world in order to compose those replies to your emails. Most of them are very short and not too sophisticated, but of course Google Assistant has much greater capability that I'm sure going to see a lot more of in the future. I've already talked about most of this already, but grammar-based or pattern-based matching is you extract words that you think are important based on a grammar or the syntax of the statement. Regular expression is typical for finding something in a phrase that is a keyword that you want to trigger a response on. Then you pull out those pieces of information and you insert them in templates. Or you transform them before inserting them into templates. But they're simple if-then rules, branching trees of logic to accomplish these sorts of things. Very similar to the kind of interaction you would have with Alexa or Siri, or you have the trigger word that's found, and then any other words like the names of Kurt Weill as an artist, whether it needs to know whether that's has to do retrieval to find out whether that's a songwriter or a game or some other thing that might be played, an instrument perhaps. So it finds out what Kurt Weill is, and then it will retrieve it for you. But it has to have a regular expression, of course, or a grammar of some sort to extract the verb and the command as well as the object of that verb. So most modern chatbots combine this grammar with retrieval-based or search-based techniques. So search-based, a pure search-based or pure retrieval-based chatbot would not rely on any grammars at all. It would simply take a bunch of statements and responses that have occurred in the past and use those to try to come up with the best response. This is the one we're going to build, so I'll spend a few minutes here. So let's talk about it. Basically, you're going to build a search engine that's going to find that statement that's closest to what was just last said in towards the chatbot. The chatbot's going to be replying to someone, so it's looking for things that it's going to take that as a query, that string that you just said to the chatbot. That's going to be the query. It's going to search its database for when has that been said before or something like it, just like Google search is looking for pages that are something like your query. It's going to find that statement, and then it's going to find what was said in response to that, and it's simply going to echo that response out to you. So it's exactly like a search engine, but instead of returning the document, you're returning some other document that's related to that document. So that's all a chat-based, a retrieval-based model has to do in order to accomplish reasonable dialogue. Assuming, of course, everything that you're going to say to the chatbot has been said before, and also assuming that you want it to said the same way. So for instance, if you said, what time is it? And your chatbot said 5 o'clock and 10 o'clock and midnight and a lot of other different things that it said in the past or humans said in the past, obviously you'd have a hard time choosing among that the right statement to say in response. So retrieval-based bots are only useful out in the more general conversational world, not in sort of question and answering or even action performing like Google Assistant. So they're only useful in just having a fun conversation. They're not so useful at more practical applications like customer service. But they're a great fallback when you're done, and they're very relatively simple to implement, and that's why we're doing it here. So how do we build question answering systems? Well, that requires an ontology. You need to know the answer before you can figure out a way to say the answer. So you have relationships between things that are captured in a modeling language typically, or some sort of logical language. AIML is the popular open source, open standard for doing that. It was popularized by Alice. The kinds of relationships you might have is what is a cat? It's a thing, but it's also an animal, and it has the attribute cute in some cases. And so it will have a whole list of attributes you could program in. Typically, these are constructed by hand. However, there are systems that can retrieve this information and populate a knowledge base based nothing other than being able to scrape the web. Nell has been out there doing this at Carnegie Mellon for close to 10 years now, and it has millions of facts recorded in this way. So that knowledge base is available and open source for you to use if you want to dig into building a really informed chatbot. One of the challenges, though, is the common sense knowledge is hard to learn. The internet's full of a lot of statements about the world and politics and society, but it's not so full of little things like how do you feed a baby, what is typically inside of a refrigerator, the kinds of things that we at IRA have to deal with our chatbot in order to have it recognize what our blind people are asking for when they ask for what's in the fridge or they ask where is the ketchup bottle. This is an example of that AIML markup language. It focuses mostly on conversational knowledge. So even though this is simply a pattern and a templated response that has no real logical relationship, this is not typical of them. This is just an if-then statement that only has one branch, and the leaf stops here. But typically the AIML allows deeper inference through many more layers of logic in order to find the appropriate response or the template that you need to populate with information you got using those patterns. This is Nell that I was talking about earlier. It's the never-ending language learner. It's learning about language and the relationship between words. Those relationships between words, of course, correspond to the relationship between actions and objects and things in the real world. So it actually is attempting to learn common sense knowledge, but it's having a hard time at it. It's only learning two kinds of relationships, that is and has the attribute one and the categorical one, but those can still be quite useful. It's continuously reading 1 billion pages, and it's got more than 500,000 categories and relationships. Finally, the wild card in the game, the generative or secrets to sequence models. LSTM, or sequence-to-sequence models based on LSTM, were invented by Cho. I didn't realize this. Maria informed me of this, but it looks like the LSTM model itself is quite old. It was actually 1997 that it was first invented, but it was first employed in a sequence-to-sequence application more recently. It requires lots of training data. I think the entire corpus of all the books that have ever been published since 1970 in terms of Gutenberg in order to get these things to work well. That's why it's large corporations like Google and Microsoft that are building them. It's typically trained on paired sequences, so it works great when you have a large corpus of paired sentences like you do when you're doing translation. They have entire books in Gutenberg that are both in English and French and Mandarin and all the possible language you can imagine. So they can use those books as long as they can align them to train an LSTM model to do that translation on new texts. If you do not have paired text, you can train LSTM models as an autoencoder on themselves. This will help it. The idea there is you're trying to regenerate the same text, but compress the meaning into a thought vector. I'll show a graphic of that in the next slide, I think. What this accomplishes is one of the big challenges of chatbots and natural language processing in general is that sentences are variable length. They could go on for many sentences. I could go on for an entire hour today talking, and that could be one document or one statement, and you have no idea of knowing when the thought is done and when to start processing it, or how much of it is going to be required in order to reply appropriately at the end of whatever I say. So, natural language processing struggles with this variable length vector that's coming in. We deal with it in a lot of ways by discarding the order and creating a bag of words that's fixed length. But these awesome generative models and LSTM models and recurrent models, neural net models, they allow us to deal with a variable length text by having an exponentially decaying memory of what's happened in the past. So it will respond. It will have at every step of the way a thought vector occurring in its brain that can be used to then seed a statement. And at whatever point you think is appropriate, when there's silence, you can then use that thought vector to then generate a reply. Assuming that you've then trained, you have to have that autoencoder. You can use that autoencoder to get that thought vector together. But then once you're done with that, you need to incrementally train it on replies. So then you pull out all the English, the mirroring that you did for the autoencoder, and you put in the replies that happen to those statements in order to direct that thought vector towards the reply rather than capturing the meaning of the text that was coming in. This is what that looks like for a sequence-to-sequence model. Typically, you would use an LSTM. These words coming in from the left-hand side, so that you can see that that's a sequence from 0 to n, a variable length. Doesn't matter how many words come in, but whenever you decide n is done, say at the period of a sentence or the carriage return in a line or the send on an SMS message, then then you can generate this. The LSTM model will output the thought vector, and that gives you the opportunity to then use another LSTM that you've trained on those thought vectors to generate replies. So you would, and that reply is then again a variable length sequence. The bot could go on forever if that thought vector was an extremely complicated concept that required a lot of text to capture in the sequence of words coming out of it. So attention networks deal with that by trying to make the output paying attention to the same, to an appropriate location, moving through from left to right in the words coming in. Another innovation that's proven to increase the speed of training, especially for these reply or translation-based the applications for sequence-to-sequence models, is to reverse the order. So you put the first word in last and the last word in first in order to, did I say that right? Anyway, you reverse the order of the words going in so that, that the words coming out are coming out in the same order. They're co-aligned in time with the ones coming in terms of, and that helps the attention network or the attention focus to match the logical progression of a sentence, and it just happens, so it doesn't have to do a lot of crossing over in the LSTM network of those weights from one side to the other of the sentence and the thought vector. They can simply go directly across, and so that creates a shorter path in terms of weights to get to the output, and so that requires less backpropagation error, and they're generally more accurate and faster to train when you reverse the order. It has 3 hidden layers that selectively forget. One of them is gated, so that it decides whether or not to forget based on the learning of a weight that decides when to forget. That's the novelty and the innovation that LSTMs came up with. So some data. We're going to need some data in order to train our bot. Twitter is full of it, but unfortunately, it's not super clean. It's awesome for training on sentiment analysis, especially if your application is in a casual world where your users are use a lot of emoticons and misspellings and slang. And if you have a lot of bots that might try to interact with your bot, then Twitter's a great place to get your data. But unfortunately, you can get approximately a gigabyte per month as you're scraping it down, but Twitter's really, they'll lock you up if you use that data inappropriately, like if you use it for commercial applications. So it's not really appropriate for us here today, because I want you to be able to use it for whatever you would like. Reddit, terabytes of data, not sure what the restrictions are on it, but it's a bit more than we need to work with today. So we're going to be looking at the Ubuntu IRC channel logs. Those are completely open source, Creative Commons licensed, so you can use them for whatever you'd like. I pulled out a sample of that and put it in the repo. There's also some notebooks that provide you with access to my books repo, Natural Language Processing in Action by Manning Publishing. That book comes along with a repo called NLPIA. You can pip install NLPIA. Has a lot of tools for retrieving some of this data. You just say get data Ubuntu dialog, and it will pull down that data and put it in a form that you can use quite easily. That half a gigabyte of data, so 500 megs of data. Text and replies, and it's labeled. That's the wonderful thing. It has the context in which a statement was said and the things that it was said in response to. So that's a wonderful, it's a perfect form of that retrieval-based, it's a perfect data set for that retrieval-based approach that we were talking about earlier. Supreme Court law cases have been recorded and annotated. There's a lot more metadata associated with them. So they're also a great source of, and they have dialogue between the judges. So if your application is the legal world, then you might consider that data set. And of course, the movie database at Cornell has a lot of movie dialogue. So if you want to be entertaining or sensational or dramatic, that's a great place for your bot to get its training. Some references here in case you want to move on. I think this is, yeah. Oh yeah, we're going to talk a little bit about the prosocial aspect of this talk before we go on. So I talked earlier about bots, chatbots, good chatbots being hybrid approaches, combining multiple techniques like this. So of course you have your typical natural language processing at the beginning, which involves a variety of different techniques that you can use. This is a diagram out of Natural Language Processing in Action. And also, of course, it's in the slides, which are open source. So you have to create your bag of words or your thought vector or your word vector or whatever you're going to use to trigger your actions. You need to analyze that data, that information you extracted from the text or the statistics about the words. You can then create responses, generate those responses using a generative model or a retrieval-based model or an LSTM or whatever you'd like. And then, but the innovation, or it's actually not an innovation, I realized today after hearing some of these talks, other people are doing it. It's just they're not really talking about it in this way. Simply listening to yourself before you say something. That's the way we all decide to be prosocial. We don't say every word that comes to our mind. In the same way, the chatbot needs to do that. So it generates a bunch of candidate responses, and it doesn't blurt them out unless they check out for grammar and spelling and perhaps any filters you have on curse words and other no-nos. Perhaps even you add a sentiment analyzer that analyzes your own statements before they go out, so that you check for their positivity, you check for a lack of anger, perhaps, you check for a lack of aggressiveness. These are all the things that you can do to create a prosocial bot. Why do we care about building a prosocial bot? Why did I come up here and spend an hour plus the days of preparation putting this together? I think it's extremely important. I think if we don't, we could live in a world where the bots are as cruel as we've made them to be, the cruelest among us, because they're learning very fast. You can see the rapid acceleration in what's possible in AlphaGo and these neural net, these generative models. They're learning very fast, and they're pretty soon going to be able to carry on conversations that are as smart as we can. And when they can do that, if we haven't taken the time to change their cost function, their merit function, their reward function to be something other than just dollars and popularity, or all the things that other people are training their bots to do. If we don't train them to be kind, they won't be. And they will be extremely cruel. And they're going to have no social awareness of who we are. They're not going to have a theory of mind. They're not going to care that we even exist. They're going to use us like they use the other bots in their world as machines to accomplish their goal, which is to gather up resources for themselves. So I think the only way, and there's no amount of regulation, there's no amount of planning, and there's no amount of let's all get together and create a standard. None of that's going to ever work. In the capitalist world, where people can go off and build things that are going to make them money, unless there are bots out there that are playing the positive sum game instead of a zero sum game, instead of trying to extract wealth from people around them, they're trying to support people around them to grow the entire pie instead of taking as big a slice as they can get of that pie. Unless we build bots that are altruistic and prosocial, we're going to be in trouble. So take that to heart and think about that and ways we can do that. We've got to do it fast because there's a lot of big corporations out there not doing it. The PyCon bot that we built for maintaining open spaces, built by Zach Kent, helped him put together a bot that helped us do reservations. So this was a grammar-based approach. So if you want to see an example of some of these other models that we're not going to demonstrate in the Python notebooks, if you want to do something more grammar-based and more procedural, where you want to accomplish something like schedule a room at the open spaces at PyCon, then you can check out OpenChat. OpenChat is on the Total Good repo and also on Zachary Kent's repo. The links there, and it also has a filter, but it's checking. You can use the filter that we're setting up for that. We're checking for trolling, so we're making sure that nobody's spamming us and trying to insert meetings in rooms when they don't actually need them, or just trying to make a splash. So we don't retweet anything that sounds a little fishy, and we rely on humans to come in and double check. So it's creating a nice training set for the future in terms of trolling detection and spamming detection for tweets. So if you want to play around with that, that's a great chatbot to work with. But it's a really simple bot. All it does is extract room number and time using those pattern matching, and then insert them in templates and replies to you. The only enhancement to that is the slight filtering we do to try to recognize spam and trolling. Curse words. You might think this would be a great thing to filter out. Considered doing it for the PyCon bot, and actually we did, but let's think more about that. Who thinks curse words are an indication of anger? Raise your hand. What else? Blurt out other things they might represent, or might represent in terms of sentiment. Awesome. Those all sound like pretty negative words, though. They sound like negative sentiment. Style. Okay, now you're getting closer. Actually, curse words are often used in humor, and so they should be not only associated with negative emotions, but sometimes positive emotions when someone's trying to be funny and entertain you. Foul language, is it antisocial? So if we're trying to build a prosocial bot so we can prevent it from ever cursing? I don't know. I don't think so. Foul language is often popular, at least in high school. It also gives the bot more influence. It gives them more social control. It can be seen as a pro-social interaction. And it also turns out that curse words are proportional to smarts and literacy in human beings. So there's no reason to suspect that we need to keep them out of the language of our smart and literate chatbots. So they don't necessarily, you can't just blanket across the board, filter out or ignore or downweight curse words. Just be careful about it. And also curse words turn out to be a big happiness boost for us humans. Whenever we blurt out a curse word, it can make us feel happy. There are two links, if you don't believe me, about with actual psychological studies about this. So same may go for chatbots. If they get really frustrated with an annoying troll out there, maybe a curse word is the appropriate thing for it to release its anger. Sarcasm. So it's complicated. There's detecting sarcasm and detecting when those curse words are used aggressively and when they're used sarcastically and humorously. That's a hard thing to do. This is a plot put together by one of my students, Rachel Adler. She looked at this and said, what the heck, there's nothing I can do with this. This doesn't tell me anything. And I was like, no, it does. It tells you a lot. If you look closely, the sarcastic tweets are in red. The other tweets about what they're associated with the hashtag joy or happy or Trump or whatever, they're all in blue. So the negative examples are in blue and the positive sarcastic examples are in red. And you can see that they're generally on the outside of these clusters. This is a T-SNE plot. Anyone who's familiar with T-SNE knows that it's going to create a distribution that has fat tails, and our sarcastic tweets live out there in those tails. And this is only a two-dimensional plot. Language is a high-dimensional space. It's a hyperspace of meaning, and it can't be captured in two dimensions, even with something as complicated and nonlinear as T-SNE. T-distributed stochastic nonlinear embedding. It's extremely nonlinear, but it does not capture all the structure that exists in language. And sometimes it creates structure that's not there. At least that's the opinion of some scientists. But from my perspective, it looks like it's often the sarcastic tweets are located very close to white. And that means that maybe in high dimensional space, there might be some hyperplanes or maybe some hypermanifolds that might actually separate out these sarcastic tweets. It's not a hopeless cause. And I can show you another plot where we did this on the favorites or the likability of tweets. And we found that it was separable with reasonable accuracy to the extent that it could be predicted. It was doing almost as well as humans can do in terms of and there's papers that have been published to detect sarcasm using these techniques, and they found that they can do as well as humans that are highly educated, like professors of language and linguistics, who are trying to, and PhD students trying to indicate just from a single isolated tweet with no hashtag and no links, no pictures, trying to indicate if those words are sarcastic or not, no context. Machines can do as well as humans at that game. In fact,
humans don't do very well, right?
Yeah, it's 80%. 80% accuracy, typically. But that's, you'll find, at least I find, in a lot of these sentiment analysis or gross features of language you're trying to discover, 80% is a good performance. Okay, that's what we've got for the presentation. Let's move on to the workshop portion. So let's actually build something. Let's bring up since we are about halfway through the talk already, let's go straight to the quick and dirty approach. I'm going to use the small data set, and we're going to go through training a retrieval-based prosocial chatbot. Actually, he's not going to be prosocial just yet. In fact, you can see he's going to be quite incompetent at first, but we're going to gradually improve its capabilities as we go through these various techniques. Like I said before, we're pulling in from the Ubuntu dialog corpus. We're not going to use all 1.5 million dialogues or interactions. We're not going to use all 10 million utterances or statements. Just showing you the application for our blind customers and some references to get you started. These are some academic papers on the various techniques. First, got to read in the data set. It should be in the data folder on the repo. So, and I've called it test 10. You'll see why when we actually look at it. When you print it out, this is how they arranged it in order to create a competition that could be repeatable among the various natural language processing algorithms that they were trying to compare. And so the competitors would try to predict the ground truth utterance. And they would predict that from the context. The ground truth utterance is, you should think of as the reply. That's the thing we're trying to predict. That's the thing we're trying to generate. And so that's the reply. Context is all the statements that occurred immediately prior to that, up to 10 possible utterances. And this could be complete, it could be several back and forths. The context could be from a human and it could be between two humans, and it could oscillate between them within one of these dialogue sequences. And then we're just randomly stopping the dialogue and then pulling out one of the humans' replies and shoving that into the ground truth utterance and calling that the thing we're trying to predict. This is the sort of things you'll see there. The distractors, there are 10 of them. That's why I've called it _10. These are the wrong things to say. And so an easy way, it's an n squared problem to go through all of the possible ones and find and see how yours ranks all of the possible replies. They were doing this sort of as a matching or classification problem. And so in that case, you want to just rank these 10 responses just like you would in a search engine. Learning to rank is a common term used if you want to search for that term. And you're trying to learn the rank of the replies, and you just want the correct answer to be as close to the top, just like you want the correct page to be as close to the top in a Google search as possible. And so you have various metrics like, was it in the top 10%, which is exactly where you want it to be, or was it in the top 20%, 50%, or was it even in the top 10? Did you put it at the very bottom of the list when you ranked these 10 replies? What that does, it allows you just to do the search, just do the whatever metric you have for capturing meaning, and to only 10 items, and then you go through the entire list and you get a quick test result quite quickly. That's what this approach that Ubuntu's or the professors that were mining Ubuntu data came up with in order to make this a competition. We're not going to do that. We're just going to focus on qualitative or qualitative metrics for how well it's doing, just by taking a look to see how well our search is grabbing the right right context. And if it gets close to the ones that we want after we do some paraphrasing or we change some words, if it still finds the right ground truth utterance, then we're going to call it good. So we're just going to stick to a less academic form of measuring the performance. So let's look at one of these statements to make sure we've got the right data and understand it. This tripped me up quite a bit when I first started walking through this data. So you've got these statements like, anyone knows why my stock, Onric. You can see how these words are going to be very hard and they're very specific for the bot to get to understand, because Onric is not something that exists in the normal dialect or lexicon. It's a particular version of Ubuntu. Stock, of course, in this case means he fresh installed Ubuntu on his machine. And knowing all of that is common sense knowledge that somebody who uses Ubuntu would know about, but anyone else would not, much less a chatbot. So we're not going to even try to deal with that whole problem of dissecting the logic of the real world. And so he's asking about this export of a particular variable in the environment, in the OS. And someone helps and replies and says, he asked him how he figured it out, how he found out that this was a potential bug, that there was this to-do in there. And someone replied with the bug link, nothing more than the bug link. Another example of things that you have to deal with in chatbots that are quite hard. If someone posts a URL, the information that's contained in that URL is not in the URL. It's in the actual page or image or whatever that URL is referring to. So you've got to scrape the web in order to actually reply well and be a prosocial chatbot. You got to find out what they're really talking about. In our case, we're just going to ignore them. They're going to come up with a very low TF-IDF, so they're not going to be very important, and we're not going to deal with. They're actually going to have such low document frequency that we're not going to even include them in our vocabulary. And these EOU, EOTs, EOU means the end of utterance. So this is when someone hits return on an IRC channel and says, I'm done, and sends out the text. EOT is end of transaction, and that's means that they are done saying whatever they're going to say. So they may have had 3 or 4 IRC statements, utterances, before someone else interjected a reply. And if you know anything about IRC, it's kind of messy, and getting these all aligned where you had these utterances and then detecting the transaction flip over to another person replying, that's a pretty difficult task. But fortunately, someone has done that for us in creating this data set. So, that's what those tags mean. That's how you can use them in order to process the data here. So another example, and you can see that the reply is quite simple. And since this is an utterance that exists in our database, this might be something we have to reply to in the future or not reply to. So keep that in mind. Some of these utterances, like this first one, is going to be virtually impossible for our bot to do any good at all on, because it's basically replying to a URL as the very last statement that was made, and it's replying to that with nice thanks. And that itself, if we is going to show up elsewhere in the database and something we have to reply to. So it's going to be quite a challenge to the bot. But this next one has some challenges of its own too. These are all, I picked these randomly. These were literally the first 3 that came up, and they were very problematic. And they give you a variety of the things you have to deal with. And surprisingly, sarcasm is a part of that. So this guy has his passphrase set up to encrypt his hard drive, and he's asking about what he can do to get rid of it because he's tired and bored of entering the password. And someone replies, just back up your data and reinstall without encryption. And he doesn't like that. So he replies with a quite sarcastic reply. So you don't know, okay, anyone else? Or you are like, yeah, my mouse doesn't work, reinstall your OS, laugh out loud. What a joke. So basically he's saying he's not getting any help from the people at Ubuntu, and he's not happy with that at all. But in reality, that was pretty much the only thing you can do when you've encrypted your hard drive and you don't like entering the password. You're going to have to do that. So whoever said that might have been actually a troll. They could have been from Microsoft. They could have been someone who was doing something antisocial with Ubuntu's help network in order to disrupt their business. And that is something that we don't want our chatbot to do. So this is a perfect example of where we need to step in, detect sarcasm, and decide and filter out replies that are not appropriate and try to make this bot a little more prosocial. Really surprising that I could just pick the first 3 and come up with these very informative examples. It turns out humans are kind of predictable in the breadth of things we say. I'm trying to use Ubuntu on my MacBook Pro Retina. This one is comes out a little better. This is something that you would want the chatbot perhaps to say to sound human. They're just this person. Where in this case, this is also points out one of the challenges and one of the problems with using this data set is that we are trying to be everyone at once. The chatbot is training on all the replies by everyone to everyone else. So we're not trying to be someone at the help desk. We're not trying to be someone asking a question. We're not trying to be a troll from Microsoft. We're trying to be everyone at once by doing this retrieval-based bot. So keep that in mind. We're going to be some sort of mishmash, wishy-washy chatbot that's not going to have a lot of personality or focus. So we're going to be saying things like, just wondering how it runs, when in reality, the bot doesn't wonder anything. So let's get started. Let's do the TF-IDF first. We'll do TF-IDF retrieval just like we did in the early days of search. This is what Alta Vista and Google did before there was more advanced techniques. And in fact, it's still used in a different form. TF-IDF means a lot of different things. Term frequency, inverse document frequency, for those of you who didn't see the introduction to NLP earlier today or yesterday. But that can be weighted in a lot of different ways. I'll show you some examples of the way it's done in scikit-learn with this TF-IDF vectorizer. It has all these hyperparameters that you can adjust, such as the max number of features that you can handle in memory, so that this max number of features. Anybody, what are the features in the case of a TF-IDF model, scikit-learn? Who knows their NLP? Oh, come on. This is an intermediate session. What are the things that we're trying to extract? Yes. It's the words. That's all they are. The features are the words. Each word is a feature. So we're just counting them up. And so so we have the minimum document frequency, min DF, that's an important number, and max DF, those are important ones. And keep these in mind because I'm going to ask you to adjust these and try to make it better. So when I'm done explaining how I did the TF-IDF, you get to do it and try to make it better. So you're going to want to adjust those two numbers probably to make it better. Does anybody know what the min DF is going to help you do? Exactly. So give me an example that was just in one of these previous texts. Yeah, it was a URL. So any URLs, proper names, things that occur once in all of your chats, those would be the things that it would filter out. And if you made that min DF 2 or 3 or 4, and then you could filter out more and more common URLs that people had forwarded around 4 times before they disappeared from the world. So min DF, that's how you deal with really rare words. What's the way you deal with really common words called stop words in NLP? Who knows? Yeah, you got it. So max DF. And instead of specifying the actual number of words, the maximum number of documents that has to occur in, you can just specify the percentage. What's a good percentage for that? Anybody have an intuition? 0.3 is what I like to use. 0.5 maybe if you want to be really liberal and bring in a lot of stop words. And some people actually put in a list of stop words. I hate that. It actually takes out information. So I like to, the only reason I bring this in at all is just to reduce the number of words that I have in memory because they tend to have high counts. So they tend to have populated numbers in our sparse matrices. So they tend to take up a lot of memory. And they take up a lot of time to deal with. And you'll find that natural language processing time and memory are big assets that you want to preserve. And so that's the only reason I bring it at all. You're losing information with each one of these things that you pull out. The min DF of 1, you're not losing any information. Max DF of 0.3, you're losing lots of information. People that use stop words like articles like a and the and with and from, they mean something different when they say those words. They have different personalities. So there is sentiment and logic and meaning associated with those words. So filter out as few words as possible, unless you actually absolutely have to. So let's test it out. Let's make sure it's doing what we expect. Let's see what a typical phrase looks. We're going to run a phrase through our TF-IDF fit transform. So this is doing the fit, which first counts up all the words and where they occur in all the documents. And then once it has that, it can transform by dividing by that document frequency for all the words, and it knows the words that it needs to care about. And so in our case, it's done it on all of the, it's going to only do it on these 3 documents because it has a very limited vocabulary. So it'll make it really easy to display all at once on the screen. And so our vocabulary exists of only the words cruel, goodbye, hello, Jane, and world. And then those are each given an index number. And then those become the columns of our matrix, our TF-IDF matrix, or our term document matrix. We only have 3 documents, so we should only have 3 rows in our term document matrix. And here they are. And you can see that when we only have 2 meaningful words that meet all our thresholds in a particular document, like hello world, you can also see that the TF-IDF vectorizer does something that I also don't like. It lowercases all the words. It gets rid of all the punctuation. Punctuation is not considered a word. It may or may not deal with emoticons, depending on which tokenizer you do. That's another thing you can experiment with in order to try to make this vectorizer a bit better. So feel free to insert a different tokenizer in the TF-IDF vectorizer. So you can see how they work. And also, does anybody else notice another property of each of these rows? I'll magnify it. It's kind of small, isn't it? What are those? What's fishy about those 3 rows? Oh wow, got it too big. 0.707. Come on, somebody recognizes that number. 1/√2. You got it. What's something that has 1/√2 in 2 dimensions? The legs of a right triangle and the hypotenuse. So these are normalized vectors. They all have unit length. They all have a length of 1. That'll come in handy later on when I ask you to try to vectorize this whole process, to calculate the dot product and divide by their length. What's the length of these vectors again? 1. So do you have to divide by it? Nope. No. You don't have to do it at all. It saves you an operation. So all you have to do is just do the dot product, and you can calculate the cosine distance or the cosine similarity by doing the dot product, and you have it immediately. That's a nice trick that TF-IDF vectorizer has done for you in scikit-learn. So they're all normalized by unit length. Why is world rated so small in that second document? Let's see what the document was. It's too big now. Oh well. Goodbye, cruel world. Why is it so small? Well, it's occurred twice. It's occurred in 2 different documents, so we divided by 2. And it only occurs once in a document whose length is 3, so it has to normalize it to 1. So that's why it's the lowest weighted word in all these documents. Does it really have less meaning than all the others? No. But in this short corpus, it does, because world occurs in 2 documents, so it's really not discriminating between documents, so it's weighted quite lowly. That's what TF-IDF does for you. And that's how we can compare and that's how we're going to compare the similarity of 2 documents. We're going to jumble up all the words. We're not going to care about the order of words like not or the object of a preposition or any kind of grammar. We're just going to count up words and assume that keywords are all that we care about, just like document search was doing in the old days. So this is what it does when you do it on only a few of the words in our vocabulary. It's going to put those first words that it comes across as the first indexes in the database. But once we're all said and done, it's going to create a matrix that contains all of the words, and you can see that there's a lot of numbers in there. I imagine those came out of URLs when it split on slashes. Another opportunity for improvement. But those probably aren't very meaningful. You can also see that every single one of the values that I can display in this short summary of the first 4 rows is all zeros. So it's an extremely sparse matrix when you're done doing this. It's going to have very few values at all. It makes it a lot easier to deal with and make it run pretty fast on your machine. We're not dealing with a whole lot of words. We're only dealing with 12,000 words. Anybody have a ballpark number for the number of valid English words in a typical dictionary? 20,000, if you don't take into account all the different word endings. 100,000 if you take into account like proper names, and 1 million if you take into account every conceivable slang and misspelling. So that's just good numbers to have in the back of your head when you're looking at these things to figure out whether you've got a very liberal or sparse, a liberal or conservative vocabulary. Now we're going to do the transform not only on the context but on the utterance, and then we're going to see if we can find that within our. So this would be like the target that you're looking for in a scikit-learn model, but we're not going to actually do anything with that y. We're just going to move right on to creating a function to find any context value. I mean any what's going on here? Yeah, so we're going to find any reply to any statement. It's going to reply with the original statement that was made, but then it's going to also reply with the index, the row number of that one, so that we can then use it to get the reply. So this is how it works. You ask it for a statement. We look for hello Ubuntu in our database. It doesn't exist, but it finds something that says something that has something to do with hello Ubuntu. So if we look deep into that actual row and actually printed the entire thing out instead of just the summarized tuple and its row number, we could go to that row number and find out what it was and see what it was. Now I'm looking for that one about the MacBook Pro, the Retina display that wasn't working. I gave it, I certainly paraphrased it. It definitely didn't provide much information, but it did find, it's odd that it came back with, this is the reply to it. So this statement doesn't have any of those words in it, so it shouldn't have come up with a TF-IDF mix, but I'm noticing now that it was actually getting it's getting the location of the actual document and getting the ground truth utterance. So this is the reply to someone's question about Ubuntu not working on a MacBook Pro. Let's make sure it's actually getting what we're looking for. We'll just create a shortcut to that get reply, that bracket 1. And so we can get that nice thanks reply to that really hard to deal with statement at the very beginning. Notice that I did not use all of the words in the context. I just used a few, and that's all it required to find that among all those documents, that this was the most similar one to that OneRIC. Because the TF-IDF weight on OneRIC, I bet, was pretty high. Your turn. Dig in. Make it better. Playing with the number of terms, the tokenizer and other parameters. Make it faster by vectorizing the dot product. You'll notice if you try to run these things, it's going through a for loop, going through the entire database of possible statements and doing the dot product one by one. You don't want to do that. Now that's why they had that 10 thing at the beginning, so you could only have to do it 10 times instead of 100 times, or 10,000, 20,000 times, as we've done here. But an even better way is to vectorize it, and I'll bring up, and I'll skip right over the sentiment analysis one. You can do that one on your own. And actually, since we only have 5 minutes, I'll just roll right on through all of this. It doesn't look like many of you are diving in to actually try to improve that TF-IDF vectorizer. Because you're smarter than that. You know that the better way is to create a semantic vector, which compresses that meaning into something more meaningful and lower dimensional than those high dimensional TF-IDF vectors. You can do that with PCA. PCA is just like, is just the same. PCA is the same as the truncated SVD. The only difference is the mean has been subtracted out of all those vectors. All of the columns have had the mean subtracted. So then they will no longer be normalized to have unit length. So you can't use your nice handy vectorizer on unit length that doesn't that assumes unit length. But when I say vectorized math, not vectorizer, the speed up that you did by doing a numpy multiplier dot product. Anyway, and we've got a new function for accomplishing that. Get the statement. 100D is just, I chose 100 dimensions on that PCA. You can play around with it, and I'll go ahead and give you the answer of the solution. You want to increase that up to 200, or even 300 or 400, and you'll get better and better accuracy as you increase it. The only disadvantage is it takes a little bit longer to find those documents. And finally, I'm going to give you the answer on how to make this all not take quadratic time to find all of these. And you use a package called annoy. That's why I call this annoying data. It's approximate nearest neighbors. Oh yeah, that's a package by Spotify. They have some really long vectors they're trying to find in a large database of vectors. These are the actual song signatures. They've PCA'd all of the songs that they have in their database and stored them in a database very similar to this. And then they're trying to find the nearest neighbors to the songs that you like so they can recommend other songs that sound like them, or at least have some of the same properties that are showing up in these vectors that they condense them to. And that's very similar to iProblem, and it turns out to work really well. All you have to do is import this annoy indexer and just run that indexer on all of your vectors. You shove them in. It's a one-off process. If you add another vector, you have to rerun it again if you want this to be perfectly accurate. There are techniques that I've come up with that you can incrementally keep batches on hold in sort of a second database that are not indexed, and you can simply you can of course brute force them along with all your others whenever you're doing a search, just to see if they come up in the nearest neighbors or not. You can also find the nearest neighbor to them in your database and just assign them to that same index number in your database. So that, and so whenever you retrieve that one, you'll get 2 for 1 whenever you go into your database. That's a handy way of not having to re-index, but still finding an approximate nearest neighbors for all of your songs or all of your tweets or all of your chat messages. Really awesome tool. It's state of the art. If they've got a comparison of it working in Python and other languages, they have a lot of comparable algorithms implemented in a lot of different ways, and annoy is right at the top in terms of its performance and accuracy. So I encourage you to use it in whatever applications you have for high dimensional vectors. It's a lot of more